So now that I know there's two factors, I can do something called multivariable linear regression. The other ones were all just on one factor. Now we combine the factors and we say, I'm going to do linear regression. What's my energy based on both seasonal, outdoor temperature, and process or my production levels? Wow, pretty good. So when we combine these two data, now I have a very good straight line. My R square is less than what it was. Again, don't focus on R square, focus on the line. It's nice. It seems to match nicely. So you have a pretty good model to explain where your energy is going. The way I look at R square, 0.87, that tells me that 13% of the energy that I use is not explained by these two factors. And if I know that I don't use energy for anything else but seasonal and production, that means that I have 13% waste in my system. That's all you have to look at. This is not going to tell you where the waste is. It's not going to point you to the northwest corner of the building to look for the valve. But it will tell you that 13% of what you purchase is not used for what you want it to be used. And now you may say, well, that's good enough, or that's not. Let's investigate. But it gives you pointers. Again, linear regression doesn't have to be complex. This is the output for linear regression out of the Excel. Most of you will have Excel, and most of you will have data analysis pack available on Excel. This is the output. If you took the table that I had at the beginning with the month, consumption, production, and outdoor temperature, put it into the linear regression formula in the Excel, this is what you would get out. It will give you everything you know. P-value that will tell you if your model is actually statistically valid. Coefficients to define that straight line. R squared, the famous R squared that everybody's holding on to. And it will give you something called predicted natural gas consumption. What model thinks you should be using given the inputs you gave it. Okay? This is as simple as that. I think it's like 5 clicks on the Excel to get this. So if you look again, the same data, month, natural gas consumption, outdoor temperature, production data, and now I added this predicted value that Excel gave me. Excel told me this is what I think you should be using in those months. I just put it into this last column now. And now I'm going to put that into the time series, these predicted values. This is what model is telling me I should be using. You told the model, this is your outdoor temperature month by month. This is my natural gas consumption historically over 3 years. This is the level of production of those same time intervals. So if it's monthly consumption, it's monthly production intervals. This is what I think this should be using. Energy consumption model or energy model. There's many names in the marketplace when they sell you software. Energy model is one of them. Well, that's what it is. It's unwrapped predicted values from the spreadsheet superimposed on your actual consumption. And now you can tell there is a little bit of a spike there towards the end there, where you're using far more natural gas consumption than the model is predicting. Those are the things that energy model can do for you. Very simple. Again, doesn't have to be complex. It doesn't have to start from the overall facility. You can start on a small production line, one line. You can start on a boiler room. You can start on a dryer. You can start on many different places. Start and prove the system. So now what Jeff is going to show you, now that we have the data for what predicted is supposed to be, Jeff is going to do a little bit of an exercise with his magic machine, and we're going to put a little bit of a flow restriction at the end to show you how this software actually registers that flow restriction. And then we'll come back and we'll analyze the data that came out of that. Okay? So let's start with it.
So now we have a completely operable data acquisition logging system. What I'm going to do is turn on the blower. It's going to provide a flow. Past here, we're going to be able to read flow temperature and a totalized flow value on this meter, on this controller, and we will also be able to see through the net meter Omni on the computer screen the very same readings. They will be sent through the net meter, through the router, and then to a computer screen. This computer screen can be remote. It can be, you know, on a laptop right beside the meter if you want a spot check. You're really limited by only the infrastructure, the intranet that you have available at site. So most sites now have a fairly robust Ethernet system, so you'll be able to log in from anywhere and see this data. So right here we have the flow ramping up. It's about 2,000 cubic feet per hour. You can see here that the temperature is dropping a little bit as we push more air through. The totalizer is incrementing as we expect. And we can also see here on the laptop screen that we have very, very, very close flow and temperature values to what we're seeing on this screen. They change in lockstep. For example, when you restrict the flow, you can watch when the flow is restricted. You can see the flow dropping here. You can see the flow dropping here. So this is all in real time. The interval is very short for this example. However, it's also user selectable when you calibrate the outputs on the NetMeter software. But you can also log this data. It's been logging this whole time, so we can now go in to the data log tab. We can load the past hour of data. We can load the past hour of data and plot on two separate axes the flow, and then we will be able to see when I turned it on, when I restricted the flow, when I let the flow back to normal, and when I shut it off. You can also see the temperature. It didn't really change too much here. This data is also exportable to Excel. The NetMeter Omni dumps to a CSV file so that you can take that data into Excel, slice it and dice it however you want, perform regression analysis and such.
So now you guys have a model, okay? We build a model, we have regression, you have consumption model, and it says, oh, you know, I'm good. But as you noticed, if you stare at that screen all the time, you will notice something's going on. But how many of us have really time to stare at the screen? Not many, I hope. And even if you stare at the screen, once it gets really complex, how would you know if you're on the target, above the target, below the target? You would have to have a brain equal to that power processor. And that's not going to happen. So we have regression. We have the expected model. We know what we are supposed to get. But the meter only gives us instantaneous readings that get bunched up in a time series, and we see it as a one big graph. But how do we know when consumption starts going off the rails? What will tell us that? For that, we need a different model. So we need a model that will tell us what the target value is, what's predicted energy. We need something that will tell us what's current reading, what's your meter reading. We need something that's going to calculate the variance between the two, the difference between predicted and instantaneous. And we need something that's going to keep a running total of those two. So now if you have all of that, mathematicians will call that cumulative summation of variances, or the famous Cusum graph that everybody in energy management has heard of or at least knows of. But that's essentially what it is. It's used to detect change and quantify the improvement. That's all Cusum is. takes the difference between what's predicted, what's actual, and keeps a running total of that. That's all Cusum does. And how it works, this is a simulated data. These dates down on the bottom are simulated. The numbers are out of this meter that Jeff has built. So over a period of time, we monitored the output, and we got this. So don't pay attention to actual number. Actual number is not all that important. Dates can be any dates for your information. But this is very similar to what will happen every single time you install the metering system of any sort. 1 meter, 10 meters, 100 meters. This is what you're going to get. You will go through a period of calibration. You will install the meter, and then it will be like, wow, this is not what I expected. Oh, the wire is not in. Oh, wow, my factor is off by 2. That's normal calibration. So you'll go through that period, you will find out what works, what doesn't. Then you'll start fairly stable period, and you use that for baselining. This is the time where you use baselining. You don't want to baseline over here because your baseline will be worthless. You want to know that your data is valid, and you want to know that the data is going stable for a little bit before you do baseline. Energy driver. If you have energy driver that's seasonal, this baseline must extend much further than this one. Then you'll go on the period of a stable run. You say, now I know what to expect. Let's see how the system works. Let's let it run as it is to see if everything works. And then you'll get to the heart of it, action. If you never got to this, let me see. If you never did this, your consumption would constantly go straight. It would never change. This is true no matter how expensive your energy management system is or how much time and effort you spend building it. If you don't change, if you do not implement something, your energy will stay remarkably stable, regardless of the investment. This is hard. This is what we are paid to do. This just tells us how good we are. This actually makes a difference. So in that baseline period, let's look at a little closer data. This is what actual consumption looked like. When Jeff measured his output, this is what we got. This is, again, very typical. Your meter will not always read dead straight. There will be ups and downs. These are very small, relatively speaking. It goes from 1820 to 1860. It's not a big change. But the proof that any graph, if you look close enough, is not straight. So now, if this is your actual, you run regression over that period of time, this happens to be 2 months, this is what the model is supposed to say. This is my predicted energy. Model tells me I should be there. And you will see that this model is actually running through pretty much midway between all these things. So if you left this to operator to stare at this and this line, how would you know if overall you're up or down? You would have to calculate every single instance instantaneously and figure out whether you're up or down. That's why you can't do that with the operator. That's why you need a model and you need something to tell you when you're getting off the rails. So again, 2-year time period, we went back. Now that we had that baseline, I took out the calibration period. This is your predicted output. Notice again, 2-year time period model, because in this period when we baseline this, we don't know what kind of implementation we're going to have. Model says you'll be using this much energy no matter what. And if you don't implement changes, that's what you will be using. So now the Cusum, we go back to this Cusum thing. Because we cannot tell by naked eye whether we're up or down on the target, especially over that period of time, what we need is something to tell us when we're getting off the target. This is what the Cusum is, that sum of those variances. You can see that here, it's baseline period. Then we go into the stable run. Then we start implementing something. This is first implementation. You can tell that we're dropping. We're going into negative. It means that we're using less energy than the model predicted. And the angle of this line tells you how good your measure was, how impactful it was. Then over here, there's a different angle, ever so slightly different angle. There's another measure that we implemented. We now use even less energy. And then we did something really good, and we drop off the edge here. Now we're talking. Now we saved all this energy. Look how good we're doing. Then we did some smaller change, angle change, but we're still doing well. So if you look at the Cusum, it tells you how good you've done stuff. And if you're doing big capital projects, this is what you're supposed to see, these type of drops. But if you're doing small operational changes, if you don't have money this year for capital projects, this will be a very small line here. Go and change all your filters, make sure that all the valves are in the proper setting, and you will get change here. And if you keep a log over here, what you've done on which date, you can go back and you say, oh, changing the filters did this. Now I can quantify. Now I can say, I have to change the filters. They're expensive, but it's worth my while changing them every 6 months because this is what I gain. How else would you do that if you didn't have this kind of model? Virtually impossible to quantify the impact of the filters. But this allows you to do that.